Well, I'm going to talk. I mean, it's a little bit strange to have this talk follow the previous one, because the previous one is so important about what's happening both in the U.S. right now because of the change in administration and the kind of unwinding of the structure that we've had for the last many decades, and it's so disorienting. Right. I mean, every day I wake up and I mean, well, particularly from here, because I'm always lagged, 4 or 5 hours from what's happening in the U.S. and seeing some new thing unwind, right? But we know it can't last because, we're on the right side of history. That's what we're trying to do, right? But at the same time, I'm going to talk about AI, and I'm going to talk about the big transformation that's likely to happen. It's not anything that we can actually prevent. I mean, in fact, if we took all the money that we could muster among ourselves to try to change the trajectory that AI is on the planet, we will fail. I mean, this is an inevitable transformation. And so what I'm going to try to talk about is what we think is going to happen. And I'm not going to say so much about what to do about it, because I think it's almost like a tsunami, and you've got to figure out how to ride the wave. Although I know it's like you don't really ride tsunamis because they kind of go in the wrong direction. But the transformations that are going to happen in the next, say, 5 years are going to be profound. We've seen, and even in the last 6 months, how much progress has been made in AI, right? 6 months ago, we were not talking about reasoning models. I mean, we knew that OpenAI was working on things. We knew that others were working on things. But in October, some of us had previews of the reasoning models that were coming out of OpenAI, and we were kind of blown away by the idea that we could give a high-level problem and the model would go off for around 5-10 minutes and generate, and generate some amazing result that would have taken us a few hours, maybe a day or something to do on our own, right? And that was kind of a hint of where we are. So I call this talk The Ramp, and you'll find out why I call it that in a minute. Some of you might know this quote, right? Babbage, who was a good friend of Ada Lovelace and so forth, was trying to build, he built eventually the difference engine and so forth, but before that, he was an engineer, mathematician, and worked on things. And I love this quote because it's kind of timeless in the sense that we're all trying to do hard computational things, and we're always looking for that next level of automation, the thing that's going to somehow free us from the drudgery of what we're doing. And that drudgery might even be right now, writing great Python code against a high-level API. It's a lot of fun the first 200 times you do it, right? But the 201st time you do it, you kind of hope that maybe there's some other thing that can take care of that. At some point, this idea that even thinking about the problem may be too much work, right? That we want somebody else to take care of it for us. That idea has been called superintelligence. And I have a whole talk about that, which I'm not actually doing today. It's in some sense a much funner talk. But it's not, it's a much more scary and emotional talk. But I think keep that idea in your head, right? That the trajectory that we're on from the visions of AI back in the 50s or 1960s, which, nothing really worked, right? A little bit of progress in neural networks, maybe 10 years ago, things started to work. OpenAI figured out that transformers actually kind of worked. They said, well, what the hell, just scale them up, right? This was the kind of the magic, right? Deep learning worked. We figured out if we scale it up, it gets more powerful. You run the scaling laws up. Scaling laws are still going strong, actually, by the way. If you keep projecting that out, maybe in a decade from now, we will have AI systems that are, for most digital tasks, better than everybody in this room. And if you keep that progression, we'll have eventually systems that are better than everybody on the planet working together on a system. And at some level, that's like really inspiring, right? Because what can we build on top of that capability? On another level, there's actually, you could think of it as a grand conspiracy to get rid of people in the grand scheme of doing things. And I think we need to, talk about that, but I'm not going to talk about that in this talk. But anyway, this idea that superintelligence is an idea that eats smart people, we see this as the basis for new companies, and we see it as the basis for big debates. And in the US right now, you could argue that that's actually what's behind what's going on in Washington. It's not about democracy or anything like that. It's about what is this idea. We'll come to that. How many people have played with OpenAI's deep research tool, the new one that came out last week? Okay, you should do this. Find some way to do this. So this is a tool that you give it a high-level task, and it can go out, it uses the internet, it can read papers, it can read websites, it can read journal articles, and so on. So you can give it a high-level task, the same thing you would give a graduate student, or maybe a postdoc. So this is a thing I did last week. I gave a version of this talk, and at the top I said, I can't even read it here, so something like, please write a report on, well, you can read it, on basically the evolution of large language models in synthetic biology. Okay, so as we hear, this is like, nobody's written a paper like this, right? So the model comes back and asks me a bunch of clarifying questions. I'm like, okay, so I answer those questions. And so I give it another paragraph, and off it goes. On the right-hand side is this little sidebar that pops up, and you can click on two different things. One is like a play-by-play action of what the model's doing to try to answer my question. And it's just going away. It's giving me kind of this internal monologue of what the model's thinking as it's doing it. And it has a little progress bar in the bottom. And after about 10 minutes, it writes a paper. The paper is called The Evolution of Large Language Models for Synthetic and Systems Biology, from 2018 to 2024, 10 minutes. It's a 20-page paper. It's actually pretty good. I mean, if my postdoc had written it, I'd say, okay, that's kind of a B+, right? We could tweak it up, publish it next week. 10 minutes. I don't know how much energy it took to do that. I don't know how many bodies are on the floor, not eating rice or something because of that energy, but this was like kind of a mind-blowing thing. And whoever's running the scheme, if you could, yeah, great, thank you. Great tables and so forth. Now, you can even tell this to produce a LaTeX document, so you can drop it into your favorite LaTeX engine, and looks beautiful. You can ask it to do math, it'll do math, right? So, in some sense, this is the picture of where we are. And if you could exclude the United States for the moment, because, we're kind of in this retro situation, but we'll fix that, in the next election. We hope, if we still have elections then. You guys are really cramping my style here. Okay, all right, great. All right, so, we've had all this progress, and we're on this cusp of some amazing acceleration. And if we weren't so depressed about, where we are, this would be like a great moment, because almost everything we want to do in science, in medicine, in art, can be built on that curve, right? The question is, can we do that, and what does it actually look like? A friend of mine, I'm going to not include his name because the reports that we're working on right now are pretty controversial in terms of how this might work, but I think it's probably useful to lay out some of the logic. So we've been working with the major AI companies in the United States, one in France, and one in China that we can't talk about, trying to figure out what's going to happen in the next 3 or 4 years. And this is probably the most succinct way we can describe this, right? About a year from now, almost everything that we do on a daily basis in this room, AI can probably do a pretty good job of it. A couple of years from now, they'll fix the projector. Sorry, guys. I mean, I love you back there, but I'm trying to, okay. So what we're seeing is a couple of years from now, and because of the progress, the rate at which progress is being made, I was writing a version of this document for my university, and it's pretty likely that most of what our research faculty do will have a substantial AI component in the next 2 years. But within 5 years, it's not even clear that we will have anything left to do. I don't mean that in a hyperbolic sense. I mean, this is like an actual prediction of what it's going to be like 5 years from now. Now, one version of this is that we get to hang out at the beach or in the mountains or something, right? And we have universal income. Hopefully it's big enough. And, you know, things might be okay, and we can work on our social justice goals and so forth. But it could be very different. And I'm not sure which way it's going to go, but I'm going to talk about how it might happen. So, a couple years ago, I was asked to give a talk about the next 10, 15 years, and I packaged it in this concept I called EasyQ, right? Exascale, AI, zetascale, and quantum. And I put it in that order to try to convince our funding people in Washington to not get it out of sequence, that quantum was not going to happen next year, that the big thing we need to worry about right now is translating what we've built in exascale computing into actual useful science, focus on AI, figure out how to scale up the next 3 orders of magnitude, and then if we're still around, then we can worry about quantum. And that's kind of the sequence that I think is actually going to happen. So sometimes you'll see this little logo here. When we were building the exascale initiative inside the US, it took a long time to do this, and it seems a little bit weird to try to connect it to these long kind of historical arcs, but it took us 7 years from the first time that we held a workshop on the feasibility of exascale computing before we had any money. 7 years. 7 years of going back and forth to Washington, telling people, rallying a community, convincing people that, yes, we could build these machines. It's not going to take a gigawatt of power. Of course, now we're talking about gigawatt data centers. But back then, the idea was this is feasible and possible. We just have to keep working on it, right? And we're kind of in that space now, a bit. But what's interesting is that industry has taken over. It's no longer the academics driving the conversation. Industry is actually driving the conversation. The question that we're being asked is, are universities going to matter in the future? Are national labs going to matter in the future? That's actually a real question, right? And we'll come to that more in a minute. I threw this up. This was from an article that was written about me a couple years ago. And I was trying to explain what it's like to deal with multiple administrations, right? I'm like, you're making the same argument over and over again, right? You're trying to re-educate everybody. There's a new administration comes in, you re-educate, you have a plan, you refine the plan, you make a better plan, right? It sounds like what we all kind of do. We managed to actually build exascale computers. In the US, actually, we have 3 of them in the national labs, and there's kind of more exascale machines out in industry, although they're not running in the same way. Mine's the Aurora system on the left. Frontier is at Oak Ridge. If you were to come into my space, that was kind of me in some weird photographer-induced pose. The machine is actually 166 of these big Cray EX racks, right? They're kind of this big. They're 400 kilowatts apiece, 166 of them. So you got row upon row like this. The blue and red tubes are liquid cooling, color-coded for the, dim. And our machine, in fact, is very similar to Oak Ridge's machine in the sense that, they're both in the same rack infrastructure, but they're kind of fun. We have 10,000 of these nodes. Each node's got 6 GPUs, 2 Intel big, Xeon CPUs with about 6 cores times 100,000, times 10,000. It's a large number of cores. Node boards are these big planes. They're plugged in kind of vertically. They're heavy. They're about 70 pounds. In fact, we're not supposed to lift them, right? It's too heavy for a human lift. So we have cranes that we built that, you put them in and lift them up. And when we were assembling the machine, everybody had to wear hard hats because it was somehow the idea that these blades would fall on your head or something. Aurora took a long time. Intel kept changing its mind. They still keep changing their mind. Who knows if Intel will even be around next year. But eventually we got this machine built, right? It's 20,000 CPUs, 63,000 GPUs. It's huge. And it went into production about 3 weeks ago. So we have lots of people using it. We did spend a lot of time trying to benchmark this thing. It's actually a machine capable of around 2 exaflops, but to actually have the machine stay up and to benchmark it to get like a top 500 number took many, many weeks. And after a while, we just gave up on getting numbers higher and higher because it took a lot of time. But we did run a mixed precision benchmark at a kind of 10 exaflops, which is kind of fun. And it does find other benchmarks. What maybe is not so understood about this is right above the machine room. So the machine room it's big, it's kind of 10,000 square feet. But right above it is this. This is a power transformer room. It hangs from these trusses. There's no columns in the machine room, right? So we have complete flexibility how we lay things out. Each one of these transformers is a 3 MVA transformer, so 3 megawatts. And we have 20 of them. A little pool, the metal container around it is to contain the oil if they somehow sprung a leak, right? These are all like above you. So imagine you're in this room and there's this basically 600, I don't know what the weight is. It's heavier than like a Airbus 380, okay, kind of hanging up there, running power. We drop the power straight down from these into the machine room to minimize the amount of copper. Somehow minimizing the amount of copper was like somebody's idea what was important. So in our world, right, in the national labs and kind of in the academic space in the US for science, open science, we have about 100,000 GPUs. That's more or less as big as Elon's machine in Memphis, right? Or smaller than some of the machines that Google and Microsoft have. Our goal, of course, is so, as we built the program to build these machines, we also had a very large-scale R&D program called the Exascale Computing Project that some of you probably knew about. That was about $1.8 billion that was invested in people. In fact, some of the software carpentry's effort was funded by ECP, so we're very proud about that. It funded 2 big activities. One was to build the system software stack that makes these exascale machines work, and that's entirely open source, and it's available to everybody on the planet, basically. The second thing was to fund about 25 major application projects. So that $1.8 billion over 7 years was split into system software and applications. So when you add that up to the cost of the machines, it was about 50-50. About half the money went into software, system software and applications, and half the money went into hardware. And there's really no way to actually get out of that box. So whatever you're spending on hardware, you need to at least spend the same amount on software. But what we can see now is that over the next couple of years, we've got to go much faster than this. We're going to have to build the next generation of systems. We can maybe push double precision flops, maybe a factor of 10, but none of the vendors want to make that. Nobody cares about double precision anymore. Nobody actually cares about that. Everybody cares about low precision for AI. We talk about AI, they're very excited. They want to build a zeta scale machine for us by 2030. So one of the things that we're trying to figure out is like, what are we going to use this for? Probably the most important, this is probably the most important slide of the entire talk, which is that the way that the US is allocating time on these machines is completely open for people in New Zealand. Right? We have this program called Insight. About 60% of the time on these machines at Argonne and at Oak Ridge is available for open science. And with a few exceptions, Iran, Syria, a few places, international proposals are welcome. So I know that you're trying to figure out what you should build here, but in the meantime, you should write some proposals and get some time on this machine. And we can give you time actually in a day through discretion. So you want to take your code and try to scale it up. Just a couple emails, you can get on this machine. I'm serious. So the world is actually much flatter than you guys might imagine in the sense of getting access to this stuff. So please do that. One thing that we're trying to figure out is how much of this machine can we allocate to AI, and how many large-scale foundation models in science can we build given the amount of time that we have on this machine. And I'll say a little bit more about that in a minute. One thing we're looking at is the future is not going to be traditional modeling and simulation applications using 64-bit without people doing clever numerical analysis to do the right errors. We don't see that as the future because the hardware is going to move towards low precision, and we know that if we do mixed precision in applications, we can get a lot more performance. In fact, my machine is 10 times faster in mixed precision than it is in single precision at FP64. But when we build AI models, surrogate applications, that is where we take a machine learning kernel to replace the computational core of a traditional application, right, that might be solving some time-dependent PDE problem, we can get acceleration like 1,000x or 10,000x. In fact, in my drug design work, we get accelerations of 100,000 by using ML kernel as opposed to the original algorithm. So what we see going forward is a huge push towards things like surrogate models, end-to-end AI replacements for applications, for traditional applications. That's just happening. We're trying to figure out what does that mean for the architecture and so forth. I'm going to skip past this. One way that we're thinking about the story that we've been telling on the Hill in Washington about how we could take the assets we have and use them for doing AI for science is something like this chart here, where we have, if you look at the models coming out of Anthropic or OpenAI or Google or something, they're models mostly trained on text and code corpora that are from the internet. There's a ton of data that's behind, not paywalls, but just random institutional data infrastructures, structured data from experiments, and so on, that's not available on the internet, people can't train on. One of the goals here is to try to figure out how we capture that into a way that we can train models, use the machines that we have, create models, open kind of foundation models, and then engage the community in building a diverse set of applications for doing science. This is where we were kind of a year ago in our thinking. It's evolved a bit, and I'll talk about that. What I'm going to try to do next is scare you a bit. So, lots of people are not yet understanding how AI is going to transform science, or even how AI at the large scale works. And I will try to give you a mini version of this. There's many great lectures and YouTube videos if you're trying to understand this stuff. But I'm going to talk about transformers a little bit. I'm going to talk about scaling laws. I'm going to talk about how we actually measure, in some sense, the battle between the big producers of models, and then what's happening with reasoning models and how we imagine we're going to build an infrastructure on top of that. So you might have seen this chart, okay? So this is a benchmark that was created last year that's supposed to be graduate level problems that you have to be a PhD in some domain to answer. And this arc here, and you can read the scale, right, kind of 90% at the top, this is what would be required, so that 90% level is what a domain expert, a PhD in some domain, chemistry, biochemistry, whatever, could answer if they had access to the internet and the questions, okay? And if you go back in time, right, models were really crappy at doing this. Suddenly, in the last 6 months or so, leading edge models like OpenAI's O1 and O3 models can now answer these PhD domain-specific questions basically at a rate that exceeds that of humans. So in some sense, what's been built are models that in very specific science domains are now better than 90% of humans. I don't think people have understood this yet. And this is kind of what Sam Altman talks about, is that the AGI is kind of going to happen, and then people will realize that it's happened, right? And this is where we are right now. This is from Sam's discussion on the intelligence age. You've seen probably this paper from a few years ago. This is from Stanford on the notion of a foundation model. I'm not going to spend too much time on it. I'd rather you actually, if you're going to take a picture and read something from this talk, you should read this white paper. On the right here is Leopold Aschenbrenner. Leopold is, I think he's 23 now. He was at OpenAI for a couple of years. He's now a venture capitalist. Last spring, he wrote this white paper called Situational Awareness. And what was really amazing, it's about 100 pages. It's a pretty fast read. It's a pretty amazing read. He laid out what was the zeitgeist in Silicon Valley. That is, what do all of the big tech and VCs think is the trajectory of tech? And he captured it in this document, but I'll explain it in like a couple minutes here. So first of all, there's this chart. This is an interesting chart. So this is an attempt at taking progress in AI and translating it into a notion of effective compute and putting it on this log scale, saying that basically if you go back to 2018 to end of 2023, there was about 6 orders of magnitude improvement of the effective compute in models. And that got us from kind of preschooler level models like GPT-2 to something that's more or less like a high schooler, GPT-4, at the end of 23. And like everything in Silicon Valley or anything in computing, people say, well, let's just keep projecting, right? So they say, well, if there's some linear projection, by 2028, we could get another factor of 6 orders of magnitude. And you can kind of imagine what that scale looks like. You have a high schooler, maybe we'll get a undergraduate, postgraduate, and so on. Of course, the ultimate goal for these companies is to automate AI research. And you'll find out why in a second. And this was kind of, you look at this and you say, well, okay, this is, a little bit weird. It's kind of just linear extrapolation. But this is actually not the chart people believe in. This is the chart people believe in. That we will go along for a while, and at some point we're going to discover some new tricks. And these new tricks will put us on a steeper exponential than we're currently on. And it's hard to imagine that because we're already on a pretty steep exponential between '01 and '03, just a few months later, right? And we're kind of climbing this thing. But this is the curve that people actually in the valley believe. I mean, I say this in a vague sense, but this is OpenAI's mantra. This is Anthropic's mantra. This is xAI's mantra. This is DeepMind's mantra. This is the curve that we're actually trying to make happen. And like Moore's law, it's not a natural phenomenon that is going to happen. It's a collective effort to make it happen. And this is what's motivating folks. And this is why when DeepSeek R1 was released, a couple of weeks ago, everybody was freaking out because it looked like we were upticking on this kind of curve, right? It takes a while to get your head around this curve. This is a log scale. This is an exponential, hockey stick on a log scale, which should make most people that believe in physics should say this is bullshit, right? The problem is it might actually be true. When you double click on it and you try to say, well, how can that actually happen? How can we get another 5, 6, 10 orders of magnitude on top of where we are right now? Well, somewhat's going to happen from just scaling compute, maybe another couple orders of magnitude. You saw Stargate announcement 2 weeks ago, $500 billion, gigawatt scale data centers, million GPU scale systems. That's a reality. That's the trajectory that we're on building out. That gets us the blue part, right? We're starting to see a lot of little ideas about how to improve sample efficiency in training models. That's the green part. What's that pink part? Anybody heard of test time scaling? Using computing in a different way to improve AI models? That's the pink. And it's wide open. We've not exhausted that at all. The idea is that these things are multiplicative, right? They're on top of each other in terms of scaling up. So this is what people are trying to do. How many people have played with code on transformers or taught this in your classes or something? Okay, all right. So I don't have time to go through this. Just imagine that we actually know how to do something, okay? We can take text, we can train a model that can do two things, essentially. It can read text, it can figure out the relationship between different parts of text in terms of semantic coupling. It can do that pretty well. That's attention. That's how in terms of like a linear sequence of text is how this part of the text connects to this part, okay? The other thing that the model does is through a series of feed-forward networks, you can think of a trajectory in the model as adjusting the semantics of each token in a very subtle way. And all of these layers of the neural network adjust those semantics. So by the time that you ingest a sequence of text, you're trying to predict the next token, the model has figured out what that token relates to, and it figures out very precisely the semantics, the semantic coupling, actually, of that next token to the previous things that it's seen. And that's what's going on in this model. And we can train it because we can predict the next token and we can figure out if we're correct or not. This is self-supervised. It's causal. We adjust some loss function, we get some feedback, and we tweak. Okay? And this is what's happening. And of course, you can train this at large scale, big models at a trillion parameters and trained on large corpora of maybe 10, 20 trillion tokens. And at the end of the day, you end up with a model that is a pretty good simulation in some sense of what it means to think, right? So I've kind of gone this. So we're going to, self-supervise, we're going to train it. We can take that base model and we can tune it on a domain. This is kind of the foundation model idea. We can give it a little bit more biology expertise or chemistry or material science, and it will actually improve its performance on those things. In fact, this is now a well-understood engineering process. We have actually a research project at Argonne called Aurora GPT, where we're using Aurora to build such models, right? And not because people haven't done it, but because we're trying to internalize the technology and have complete control over what we train the model on, how it works, and so forth. And lots of places are doing that, right? So it's not people complain about OpenAI or Anthropic having closed models, but everybody understands how these things work, and we have our own models. So you're going to produce a base model, you're going to fine-tune it to follow directions, you're going to then give it some preference training. I want it to be nice to me, I want it to speak in some, cheerful way, right, when I ask it questions and so forth. And we produce an aligned model. And what we use, and what you're using if you connect up with OpenAI or Anthropic or something, is a model at the back end of this, which has been a raw model, then tuned to follow instructions, to behave properly in a chat, and then to behave like a friendly bot. Now, what happened a couple years ago was a realization, and this is a slide from my friends, that in fact we could do better than that. So the normal way at the top you would think about this is you'd spend most of your time pre-training them. We call it pre-training because you're going to fine-tune, right? So the first part of the training is really just training. It's a huge amount of general training. And then you do this thing called post-training, which is the supervised fine-tuning and the preference tuning. And then during inference, you're not using very much compute. In fact, for a model that is, say, 1 trillion parameters, to predict one token is 1 flop per parameter per token. So I need a teraflop per second to predict 1 token per second on a model that was 1 trillion parameters. A model like GPT-4o is 1.8 trillion parameters, but it's a mixture of experts models, so you don't actually use all of the parameters all the time. So you could think of it as a little bit less than 1 trillion parameters. So a GPU with a few, say about 10 teraflops or something, can do about 10 tokens per second in a single GPU. If you add them up, you can get faster. Okay? So the top thing is what people have been doing for the last couple of years. What was realized is that, in fact, if we tell the model to use a lot more computing at inference time, it does better. In fact, it does a lot better. And this idea of scaling up the amount of compute, not at the time you're training the model, but the time that you're using the model to make inferences, that's the big idea of the last year. It's called test time scaling. So you might have heard all these proclamations in the press, everybody's doom and gloom, scaling laws are over. No, it's not true at all. Scaling laws are doing fine in pre-training. Just test time compute right now is more effective at putting, if I have an X amount of compute, I put it in inference, I'm going to get more bang for the buck. You can actually predict pretty accurately for a given model on a given piece of hardware how much compute and how much data you need to feed the model to get accuracy that you care about. I'm not going to spend time on this, saying that scaling laws are perfectly fine. They're not dead. We actually understand this incredibly well. It's, in fact, how companies are planning how much compute they need to build to get to the next generation of models. This is well understood, very well understood. Like quantum mechanics, kind of. People are going to they're building big models, these 2 trillion, multi-trillion parameter models. These are things that will take large fractions of a year to train on 50,000 GPUs. And this is why there's not many of these. There's maybe 7, 8 companies in the US, maybe a couple in Europe, one maybe, a couple in China that can do this because they have big enough machines. And you can, attach names to this, but Olympus, is a model coming out of Amazon. You've got Claude coming out, Anthropic, which is also Amazon. You got Google, right? You've got OpenAI, which is really Microsoft as well. So there's a handful of companies doing this, and we can see that we're going to continue to make progress in making the models larger because it makes the underlying base model smarter, which then adds capability as you do test time compute expansion. So you have a base model that gets smarter, and then you throw more compute at it at inference time that even gets smarter. You see sometimes these leaderboards. These are kind of fun. I encourage you to look at these. One is LM-SIS. There's a handful of these. These are places where you connect up to them, and humans they will say, oh, do you want to give these two models a prompt? So you give them a prompt, the two models will answer the prompt, and then you choose which one gave the better answer. If you have 1 million people doing that, you've been scoring these models. It's like scoring a chess match. And in fact, they use ELU scores, very much like a chess match. So you start at 1,200, and then you battle each other, and who wins, okay? And so these leaderboards are actually battles between the models. And what's really interesting is how well the Google models are doing, even though people don't really talk about them that much. And there's different boards. I mean, they're all basically the same. And the ranking slightly shifts with time. What you don't see much is something like this. So earlier this year, there was a group of people screwing around, usually, probably after drinking. And they said, well, why don't we just give the language models an IQ test? So they went and got the Mensa, right? So Mensa, these high IQ, self-congratulatory societies. And there was one in Norway or something. I can't remember where it was from. I think it's Norway. And the guys, they grabbed the test, and they just started giving it to the models. And you can see where the models landed. So most of the models landed a little bit below 100, which was very comforting for humans, right? Except for O1, which was at 120. And we know that O3 is actually substantially better than O1. Now, what does it mean to have an AI that has an IQ of 120? Well, at least on Norway's Mensa test, it means that it's smarter than most people. I don't think that's sunk in to people yet. No, maybe it's just smarter in Norway, I'm not sure. So these reasoning models have thinking time. And the way to think about this is, for a long time, human psychologists would take human kind of thought processes, and they'd say, look, we have type 1 thinking, which is what my wife says I only have, which is, she talks to me, and then before she finishes, I say something, and then I'm always wrong. And, but it's like this whole fast thinking, right? This fast mode where you're not even aware of what you're thinking. You just kind of do it, right? And most of what we do in our kind of reaction to the world is like that. Type 2 is actually more like what we do if somebody hands us a math problem. Or you're reading your credit card statement or something, you're like, what the fuck, right? You're kind of thinking through it, right? So the question is, could we build models that actually do that type 2 thinking? Where they actually pause, they think about it before they say something. That's what these reasoning models are doing. And the question is, they're simulating it at some level, is how do they work? So the notion is that you're going to question a model, you're going to give the model a prompt, and before it outputs something, it's going to have some inner dialogue. It's going to talk to itself. And then at some point, it'll convince itself it has a good answer, and then it's going to output it. And that's the difference between, say, GPT-4o and O1 or O3 or DeepSeek R1, is that they have this reasoning step in it. And the reason that matters, and this is what I was talking about earlier, is these are two curves. This is from OpenAI. This is from O1, where they looked at, if we throw more compute on the left-hand side here, this is in the pre-training phase, and on the right is at the inference time. And you see that the steepness of the curve is steeper on the right. By adding more compute in this type 2 thinking time, the model does better proportionally. Now, it's hard to get that from this chart, but if you look at something that people actually care about, like the New York Times puzzles, okay? Yeah, or the Mensa, the same thing. You look at the models that are crushing the New York Times connections puzzle. My wife does these things. They're too hard for me. And all the models in that right-hand side are these reasoning models. And you see this exponential curve, right? The idea that you can have a model that doubles performance of a previous model in a few months is what's blowing everybody's mind, right? Is this idea that there's more techniques. How many doublings can we get? This is like tying back to like Leopold's thing. So we have, type 1 models and reasoning models. And this reasoning model, how we do this is really the interesting thing, right? we know that we can have small models, and if we just give them enough time, they will outperform big models. Not in everything, but in some things. And here's a chart here showing that these up and to the right curves are small models outperforming their bigger cousins if we give them enough time. And in fact, it's not just giving enough time. You have to force the model to take the time. It's like a little kid, right? You're like, sit down, stop moving around, do your stuff, right? If you can force the model to take its time, it will actually do better. And this is, it's kind of amazing, actually. Now, not all of these approaches are the same. You've probably heard of this idea of chain of thought. This is what is behind the reasoning strategy of models like O1 and O3, this notion that it started out in the prompt, you would say, I want you to solve this hard problem, but I want you to explain to me step by step how you're doing it. And simply by telling the model that it had to explain to you step by step, it forced the model to do step by step, and it actually got better, right? And people realized that, I can do this chain, but what if I tell it, try many options and then compare them? Or try many options and do it like a search tree, or try many things and treat it like a graph. And so the point is that the more degrees of freedom that you give the model, and the more you're forcing the model to try many things, the better the model got. And this is not changing the training of the model. This is at the inference time. So what OpenAI did was they said, let's build this into the base system. Now, DeepSeek, you've heard about the DeepSeek thing. DeepSeek guys did something particularly clever. They said, in order to train a model to think through these reasoning steps, you actually have to give it examples of reasoning steps. So you could ask a model to explain its reasoning at length and collect hundreds or thousands of these reasoning traces. Now you have a training set that you can then feed back to the model and say, this is how I want you to solve problems, by thinking through. So this is what OpenAI was doing, others have been doing it. The key thing was that you have to evaluate how well those reasoning traces work, and that results in having a second model, what's called a reward model, that can look at the output of that and say, you did a good job or a bad job. It's like a teacher giving feedback to the model. And that's a fairly compute-intensive process. But if you simplify that process to just a rule-based system, I'm going to give you a whole bunch of examples, thousands, tens of thousands of examples, but instead of having a model have to look at the output, I'm just going to write a rule that can grade it. This is what DeepSeek did. 800,000 examples with a rule-based reward scheme. So how does this work? Well, think of these little progressions here. You've got a problem, you have a thinking trace, and a solution. And you have a way to decide if the solution is correct. And if the solution is correct, you reward the thinking process. You create maybe, a large number of the PTS series. Then you go to the next step and you say, I'm going to give you the problem. I know what the solution is, but I'm not going to tell you what the thinking process is. The model has to generate that thinking process, and you see if it's correct. You reward it. And finally, you say, I don't even know what the solution is. All I know what the problem is. And the model will generate the thinking trace and generate the solution. That's the trick. And it turns out for parts of science that can be thought of as axiomatic, where you have rules like mathematical physics, parts of chemistry, right? This works, and works amazingly well. In fact, you only need about 300 examples, and only 30 of them where you know what the solution is. And reinforcement learning will actually figure out how to emulate the successful examples and bootstrap into the parts that aren't labeled. And this is what has got everybody kind of really jazzed, right? So I mentioned this is what DeepSeek did. They came up with this rule-based scheme. There's lots of papers showing that this is effective, so I'm not going to go through that. So the second thing is the notion that you can actually fake this. I know your brain is kind of melting. It's morning, and I didn't get to bed till 4, so I have no sympathy for anybody in the room. So you've probably heard of these DeepSeek R1. They're a big model, and that's what they did this technique on. But they've also produced these little models called distilled models. Like, what the hell is that? What they did is they took the trace, these 800,000 thinking traces, and they said, forget how we got these traces. We're just going to take an existing model, like a llama model, and instead of fine-tuning llama using the standard pipeline that I was showing earlier, we're going to say the way we want you to behave is to do these thinking traces. And all of a sudden you have a llama R1 distilled model that now has been forced. It's really cruel to the model, right? The model's like been forced to think all the time. And that's what these distilled models are. And in fact, that works so well that you can do something like this, right? So you take the base model, you have this reasoning data, which are these thought traces, say 1 million of them, ish. You don't even need 1 million. In fact, I'll show you in a second, you don't need only about like 1,000th of that. You then do reinforcement learning on the underlying model, and presto, you have a reasoning model. Then all hell breaks loose, right? The market loses $1 trillion because of things that you don't need computers or anything, right? And of course, they're not understanding the Leopold curve, that we need 100 of these innovations to get to a model that's 1 billion times smarter than the current models by 2030, because that's the trajectory the whole planet is on. So then comes Fei-Fei Li and her crew. So Fei-Fei's great. The guys at Stanford and Allen and so forth, they said, okay, how far can we take this? So they, instead of having 1 million examples, actually DeepSeek did 800,000 examples. They created 1,000 examples, just 1,000. They took a base model, and they did 2 really simple things. They said, we're going to fine tune it on these traces, and we're going to add a new token called you can't stop now. Okay? So think of this as, again, it's like model cruelty. The model wants to stop. It says, I did my thing, I'm done. I generated your 200 tokens, I'm done. And you're like, no, you have to keep thinking. Okay, so the model keeps going. And the question is, what is it going to do when you force it to keep going? Well, it falls back on the fact that it was trained on these 1,000 examples of these long traces. And all of a sudden, a really dumb model becomes a really smart model. And this is what's behind all these press, Berkeley reproduced DeepSeek for $50. Okay, it's all bullshit. This was the idea. And it was very clever, right? And you can see on the chart on the right that S1 is their little model, number of examples, 1,000, and it's getting like 95% on the Math 500 benchmarks. Now, why am I showing you this? Because, you might think, this is some weird anomaly, right? But if you go back to the zeitgeist curve, we're going to need hundreds of little tricks like this to climb that curve. And the community is working on hundreds of tricks like that. And they're not all that hard to find. We just haven't been looking for them. I'm probably running out of time, but I want to say a little bit about how does this relate to science, because I work in biology a lot. And the real problem with biology is it's not axiomatic. We actually don't know how to create reasoning traces, deep reasoning traces on problems in biology, because current models can't reason through biological problems. They can't reason through many things that we have higher order ways of thinking that are not easily reduced to a set of axioms. So this is one of the problems that we have. Doesn't mean people aren't trying, though. This is a chart of foundation models in biology. This should blow your mind. Your mind should be already blown like 6 times today, but this chart should also blow your mind, saying, look, we don't actually know how to do this, and so why are so many people actually trying to do it? Because the gains are huge here, right? Cancer, any kind of drug design, anything, right? Each of these little models, a couple of our models are up here on this chart, are foundation models trying to solve some version of this problem in some part of biology, either on protein folding or sequence analysis or annotation or something. So a lot of progress there. Lots of ways to represent biology in these models. I'll go through that. This is an example that's actually kind of cool. It's a foundation model. You can't talk to it in English so much, or even Mandarin. You can't talk to it that way. You talk to it in partial sequence, either DNA sequence, protein sequence, structure, or whatever. So the way you prompt this model is you give it some partial biological structure, and it will fill the rest in. So if you're trying to design a protein and you care about, say, the active site, you give it a little active site and you give it some hint about the rest of the molecule, and it will fill it in. So this is becoming routine. We can do this now. So, we think about AlphaFold giving us structure. We give a sequence to give us a structure. But this is in some sense a universal inverse function. We can give it a structure, it'll give us a sequence. We can give it an annotation, it can give us a sequence, it'll give us a structure. It's kind of, all the biology that we can just sample. And we're figuring out how to do that kind of stuff. Now we want to build large-scale scientific reasoning systems. We want to build on top of all of this technology and use it to do cool things, right? We want to build better batteries. We want to, quantum materials, whatever turns you on. We want to do it with this. And so the question is how to build such things, right? So we know that if we take a task and we give it to a bunch of different models with slightly different instructions, we will get, it kind of sounds perverted to talk about this, it's like you have a diversity of models that will try different approaches and then combine that. And this is essentially a network of agents. And we're starting to see this happen, right? So you have a human here, and you have a set of, all the rest of these guys are robots. I mean, not physical robots, but AI robots. You've got one pretending to be an investigator, one that's a critic, like the reviewer of, reviewer number 2 or whatever in the reviews, right? You've got a model pretending to be an immunologist or a machine learning person, and you're asking these models to do different parts of the problem, and then they combine it. And this is actually starting to work. And the key thing here is that all these things add on. So we have a model now that's good at reasoning, so all of a sudden these agents can not just do type 1 thinking, they can do type 2 thinking, right? And some of them are going to be good at using tools. In fact, one of the ways that you can fine-tune a model is to expose it to thousands of APIs. In fact, the standard API fine-tuning has 26,000 application programming interface, APIs, encoded in a way that the model can learn all of those interfaces. It learns the semantics of making those calls. So now you have a model that not only is at IQ of 120, it knows how to use 26,000 APIs. That's a tool use model. Now you can couple them to domains. You can know about biology, chemistry, physics, quantum materials. We're trying to figure out how to do this, like at scale. And it's like, what is DOE going to do with all these machines? Well, this is the model that we're trying to figure out. So we're going to have this strong reasoning AI. We have models, they could be foundation models trained on specific kinds of data, chemistry, material science, etc. Access to databases via these APIs. Models can now just directly call the API, no problem. They can construct codes and run simulations, and they can do experiments. Part of the API that we're building is an abstract interface to laboratories to tell an automated lab to do a set of experiments. So now you've got this notion of the AI kind of orchestrating a whole scientific enterprise in a single tool. And we can turn this on to computational science. So we have a project called Astral where we're trying to do this to automate the entire end-to-end process of doing computational science. And it's kind of fun. People are seeing different ways of doing it, combining human input, AI input. This is kind of what the master chart looks like. You've been following, again, in the Leopold zeitgeist, the holy grail. In fact, when you go to AI conferences and you ask people, what is the goal? The goal is to build AI that can do AI research. That's viewed as like the highest problem to solve, right? These guys in Japan, Sakara, they're actually trying to do this. So they have a system that's able to run AI experiments. It's completely AI-based. It then plans the experiment, does the experiment, writes the paper, reviews its own paper several times, and then produces a paper that's followed its own internal review process. These things are starting to appear in the literature. There's been some experiments about, is this good or bad, right? We don't, you can argue broadly, maybe this is the end of us, but when you give a bunch of smart people access to AI and in the right mood, it promotes some interesting things, very divergent thinking. It'll let people try things that they wouldn't try otherwise, right? It challenges their internal bias. The machine might have a different bias, but it will challenge their bias. You can use it in brainstorming and so on, and we're trying that. But the fundamental question, this is what I'm going to leave you with, a couple slides here, is given this huge curve, and given the trajectory that we're on, how do we know what to do, right? It's kind of like if you went back 30 years ago in the heyday of Moore's Law, right? You go to your computer store, and they'd say, when computer stores would talk about megahertz and so forth, right? You say, well, right now I've got this, 3 megahertz machine, but if you just wait 6 months, it'll be a 8 megahertz machine, right? And you always have this notion, well, should I just keep waiting? Right? We're now in that situation. In fact, if you're trying to figure out a piece of science to do, you have to ask the question, should I just wait a little bit? Because at the rate at which AI is getting better, maybe 6 months from now, AI can just do that problem for me. I shouldn't actually spend any time on it. And so this requires some thought, right? We've been thinking about this. So we can kind of think of the space as having 3 phases. There's a place where as AI gets better, the value of what you're trying to do gets higher. We call this kind of AI complementary problems, right? These are things where the actual value of the project will increase as AI gets smarter somehow. We have things where it doesn't matter. So a lot of things, if you're human aesthetics, art, cooking, walking your dog, AI is not going to affect all of that, hopefully, right? That's just kind of neutral. And then you've got these things where AI is going to substitute. If you listen to where the big AI companies are at, what they're attempting to do is build models that can substitute for essentially all of human labor that can be done digitally. Probably the best way to get your head around it, imagine that you're in van life, okay? You're on YouTube, you're a van lifer, you're driving around, I don't know. There's van lifers in South Island, I know. Probably living a better life than we are. And maybe they have to work, and they work via, I don't know, a Starlink channel or something. And they're doing work, but it's completely digitally mediated. That is the target of what these guys are trying to do. It's like if there's a certain amount of work, maybe it's 30, 40% of what humans do right now in developed countries, is that kind of work. That is the target of AI, and being able to do that at very low cost, right? And in some sense, the notion is that we've built the ability to take energy and directly translate that into cognitive labor in the same way that our forefathers, or foremothers, right, figured out how to take energy and convert that into physical work. So the way the world will look going forward is this notion that we can, of course, take energy into physical work, but now we have the ability to take energy into intellectual work. And how are we going to make sense out of that space? This is the weirdest idea. This is from one of my former PhD students who were having a retreat a couple of weeks ago. And Fong Fong is amazing. And I said, well, just boil it all down. He said, okay, this is the thing. It's the one-person unicorn. Now, you guys know what a unicorn is? Right? Okay, look, New Zealand's trying to be a startup economy. You guys got to get with the lingo, okay? A unicorn is a startup worth $1 billion, okay? Right? So in the Valley, it's all about creating unicorns. or multi-corns, right? Companies that are worth $3 or $4 or $5 billion before they go public. So the idea here is that with all of these AI agents and all the progress, is it possible for an individual with the right idea and enough AI to create a one-person unicorn? Now, before we just dismiss this as like crazy talk, you could flip it around and say this would be the most empowering thing that humanity's ever done, because it means that we're only limited by our ideas in terms of creating value, and we're at the verge of decoupling value from work. On the good side of that, we could use all of that value to make the world a better place, right? We can raise everybody's boats in all that sense. We don't have a social system that can do that currently, right? It just breaks everybody's brain when you talk about that. But that's the opportunity. And if you're a positivist or an optimist, technological optimist, that's what's on the runway, right? Doesn't mean this will happen, doesn't mean it'll be good, but that's the opportunity space. I think it's for all of us to figure out, first of all, do we want this future? I don't think we can actually avoid it. Like I was saying before, there's all the money in the world can't stop this train that we're on. So we have to figure out a way to turn this to our advantage, turn this to all the things that we want. Pursuit of truth, health, beauty, whatever we want. That's the opportunity. I'll stop. Thank you.
I think we will definitely do questions. Was that you, Richard, over there? Awesome.
Thank you so much. That was great and illuminating. So this will be a challenging question because it follows on the previous talk.
Yeah.
So you've mentioned Leopold Aschenbrenner. I just read his paper.
Yeah.
And he's kind of a war hawk. He cares a lot about AGI in the terms of how do we have the U.S. defense.
Yeah.
And what I want to ask is, what other voices are you listening to that aren't interested in military defense and aren't interested in technology for technology's sake? How are we building up people like the Carpentries does?
I would say that's a very good question, because there aren't so many loud voices in that space. This is part of why we're trying to talk to folks that cross over between understanding the technology and having some sense of moral compass. Because if you talk to Leopold, he's not particularly hawkish when you talk to him in person, but there is a mindset, and this is very much in his paper, but it's not just from him. I mean, if you talk to Eric Schmidt, he thinks the same way. Lots of people think the same way, that the first country to build AGI will have a decisive advantage over other countries and how they use that technology for their own advantage, whether it's military, social, economic, or whatever. And that rhetoric gets translated into a notion that if it's possible to create such systems, like I was positing, then in the US, the mindset, and to some degree in Europe as well, particularly France, is that if it's possible to build such systems, they must be built by us, because somehow we're morally superior than others, right? And that's usually translated into some Western democracy versus the Chinese Communist Party kind of story. But I think it's deeper than that, right? It's like once this technology exists, it will quickly become democratized. That's what we saw. That's one of the lessons of the DeepSeek, news cycle of the last couple of weeks, right? And if you listen to what Sam Altman's been saying, Sam's like, when they started OpenAI, the whole idea was to do this and make it open and make it for democracy, kind of democratizing progress in AI. And then, of course, they started seeing billions of dollars and, kind of vectored off. But it wasn't so much because they were trying to make money, because they realized they needed hundreds of billions of dollars of investment to do it. And in the US, there's actually no way to raise that scale of money if you're a nonprofit, right? The only organization on the planet that has maybe $100 billion is the Catholic Church. It's not a company, right? So, or maybe the US government. And so they vectored in this other direction, but he's even saying now we're on the wrong side of history. This should be open, right? What we need to figure out is if we have this, imagine aliens coming down, they land right here and they give us an amazing thing. And we're like all marveling at it, and then we have to figure out what to do with it. And we're in this weird period where we can kind of see maybe the aliens are going to land, and we don't know if it's going to be next year or 5 years from now, but it's not like 1,000 years from now. It's going to be soon. And we're completely unprepared for what to do with it. And that, I think, is the message, right? The kind of, Carrie left. I don't know what, maybe I made her mad or something, but
She's back.
Yeah. Where's she at? Oh, there you go. Wonderful. Okay. So we have to figure out how to use this for good. And it's something that everybody has to participate in. It's not for a handful of people. And Leopold may be wrong in terms of, how hawkish he is or whatever, but unless the rest of the community gets activated on this, the folks that play up against the military-industrial complex will own this trajectory for a long time. And if we don't want that, we have to do something about it.
Last question.
Yeah, this might be a bit of a downer, sorry, but let's see how we go. So one of my main research interests is cybersecurity.
Yeah.
We've got this move towards democratization of these very, very powerful tools. Yet we also have a situation where we're pretty sure that most of the software that most things run on is pretty broken.
Yep.
What's your sort of feeling about what we should do about that? My instinct is immediately to say when AGI is out there, and even now probably people can bend these tools, individuals that are at risk in the world can bend these tools to cause significant problems. Do you see a kind of good systematic way to try to build a kind of socially positive defense against that versus just hoping that it doesn't get used by the wrong people for the wrong things?
I guess the simple answer is no, I don't see how to fix it. Most big systems are broken, but we limp along because the consequences of the brokenness is not catastrophic, right? AI potentially is an accelerant on that, so it could make things worse. It could also help us fix such things, as we were talking about last night, right? I don't know which way it will go. I just know that it's going to go.